Okay, good morning, everyone. So yesterday's speaker has been rescheduled to the end of March, so that is good. And today we're happy to have Shashank teach us about some coding theory.
Okay, thanks everyone for coming. We'll talk about this decoding of codes. And in the first half, I'll focus mostly on algebraic codes. And in the second half, we'll talk more about expander-based codes. Okay. So code C data. So we'll be parameterizing codes by this rate R, which is going to be a number between 0 and 1 throughout the top. And the sigma will be the alphabet of the code. Typically, we think of sigma as some finite field. And in this case, you can ask for an additional property from the code, which is that C is not just a subset, it's a subspace. And this is called a linear code. So like sum of two code words is also in the code and so on. The other property of a code that we want is the distance of the code, which is going to be the distance of the code says that if I look at any two distinct code words, they should differ a lot in Hamming distance. I look at any two distinct strings in the code C, then their Hamming distance, and just to stress that I'm normalizing, again, delta is going to be a number between 0 and 1. Okay. So both R and delta are going to be rate and distance between 0 and 1. The quintessential example of a code is the Reed-Solomon code, which is based on bounded degree polynomials in finite field. So this is the set of all univariate polynomials over the finite field F cube of degree less than k. The code C should mention n here is called the block length of the code. This is simply the polynomial f evaluated on n distinct points. Okay. Where I'm choosing the distinct points to be 1 gamma square up to gamma to the n minus 1. So gamma is just the generator of the f cube star. Okay. So the code will look like there will be one code word for each polynomial. There are q to the k polynomials in this set or in this set. For each such polynomial, we evaluate it on n distinct points where n is greater than k. Okay. Well, from here, it should be clear that the rate of the code is k over n. Because it's a set of size q to the k. Right? So. Right. And the interesting part is the distance. We say that if there are any two distinct code words, F1, distinct polynomials F1 and F2, their difference will also be a degree less than k polynomial. And if they are distinct, then this is also non-zero, which means that it can have at most k zeros. at most k minus 1 zeros. And therefore, the distance between f1 and f2, where I'm overloading this notation f evaluated on 1 through gamma to the n minus 1, is at least scale this. And throughout the talk, I'll be suppressing constants, and I'll be only interested in terms that scale with n, because we are dealing with infinite family of codes typically. So because the rate was q over n. So distance is 1 minus r. And
Q has to be bigger than n.
q has to be bigger than n because I need n distinct points in the field to evaluate on. Distinctness is very important here. And if the finite field was smaller, then I won't be able to find n distinct points.
Delta is normalized, no?
Sorry?
Delta should be normalized.
It's just one.
Yeah, it should be.
Yeah. Okay. Yeah. Okay. So if this was the entire space, thinking of sigma as fq, then maybe these polynomial evaluations are going to be strings that are all separated from each other. So any two distinct points will be at least 1 minus r distance away in Hamming distance. Or in other words, if I start drawing balls of radius 1 minus r over 2, then maybe the ball is empty. Or another case could be the ball has one code word, but it can never happen that the ball has two code words. Okay. Let's do that. So no Hamming ball of radius 1 minus r over 2 can have two or more code words. Okay. And in this sense, codes are called pseudorandom objects because you can think of these Hamming balls as tests. And is the set of code, if we think of the set of code words, is that pseudorandom in the sense that if I choose a randomly, let's say a random linear code, then this test will say that most Hamming balls will contain 0 or 1 code words. All Hamming balls will contain 0 or 1 code words. And this is an explicit set that also has the same property. So these Hamming balls act as our test functions. Okay, we are interested in strengthening this result. How can we try to strengthen this? Well, maybe we can try to improve the radius, but that turns out to be tight. So let's quickly see why. Right. So of course, if I start changing the number of code words, then I can always increase the radius. So the right thing to do is to normalize the number of code words here, like parameterize the set by its size, and then say what is the largest ball we can choose like this. And parameterizing it by size just means that we are fixing the rate to be r. For a fixed such rate r code, what is the best distance we can have? Singleton bound says that we cannot hope for distance more than 1 minus r. Cannot have.
Yeah.
Yes. And the idea is simple. Let's pick out some Rn minus 1 coordinates out of n. And by pigeonhole principle, there will be two code words that have the exact same value here. right? Because if I fix the values here, there are only sigma to the Rn minus 1 possible assignments to the first Rn minus 1 code words. There are more code words than that. So there must be some two that clash here. And in this case, these two cannot differ on the first Rn minus 1 part. They differ on all the remaining ones. So distance for these two, let's say F1 and F2, is always so for any radar code, we can find such two code words here.
Well, in the read Solomon code, why did you use cyclic generator of this field? Why was it important? Or
Yeah, so right now it's not important because I can use any distinct points, but later on it will be important how we choose the points.
Okay.
For now, it is not important. Only distinct length matters.
Why is this called the symbol sometimes?
It's the name of a person.
Oh,
Yeah.
that's confusing.
Yes. Okay.
So one is the Christie code, after the name of a person.
Oh, really? I did not know that. Okay. Okay. Okay, so another, like if we take this Hamming ball view, then we can always construct a G. I'm thinking of the center of this ball as G, where I'll give the common value here, and maybe divide the remaining coordinates into two parts, and construct G with half of F1 and half of F2. And that's going to be the bad center. Because from G, both F1 and F2 are going to be 1 minus R over 2 distance apart. So as soon as we enlarge the ball to size 1 minus R over 2, we must have two code. There will be some ball that will have two code words. Okay. So all of that is to say that this probably cannot be improved. But maybe we can try to improve this part. Okay. So natural generalization of this would be no Hamming ball of radius, maybe more than 1 minus R over 2 now, cannot have, has 3 or more code words. So I'm okay with 2, but I won't allow 3 code words. Okay. And like even as a statement, it should be interesting because all of this was just following from the fact that a degree k polynomial cannot have more than k roots. So a generalization of that sort that involves 3 polynomials might be interesting in general. Unfortunately, we'll not be able to do it with directly this code. We'll have to modify it a bit, but let's build towards what that modification is. Okay. So we'll actually do everything in a total of 4 acts. Let's start with act 1. And here we'll at least start to learn to deal with more than 2 code words. Okay. So actually it's easier to describe what Act 2 is, but I'll prove Act 1 first. So in Act 2, we will try to construct a code that has this property, that if we look at any distinct H0, H1, these are S plus 1 distinct code words, and a center of a ball. So ball is just referenced by its center and radius, right? So you should think of this G as referencing a ball. The distance of the sum of distances of these S+1 code words is large. And some of this might give deja vu from last year's talk, but that's by design because we were talking about expander-based codes last time. And this time we are talking about algebraic codes, but the proofs have a lot of common ingredients.
You need n, right?
Sorry.
You need n here?
Oh, okay. Yeah, so I'm thinking of this as normalized. Actually, I'll be using this throughout the talk. So let me define this to be normalized. Okay, I'll just change the definition to normalized. N will always be fixed. Or I'll comment where things change.
Just wanted to say that in the special case where G is one of the HIs,
Yes.
then you get this as a depending
Yes.
on your distance.
Are
we assuming distance 1 minus R or?
Yeah, so we are assuming distance. Distance was easy to get. This is going to be a stronger property.
Right.
Because if you just take H0 and H1, that's going to correspond to distance. Right? Because
you wrote 1 minus R, so I'm asking if the distance is 1 minus R.
yeah, so the distance is 1 minus R. Yes. So yeah, S equals 1 was the usual distance. And there again, we wanted 1 minus R and we were able to achieve that using Reed-Solomon codes. Now we want more, and usual Reed-Solomon codes will not be able to give us that, or at least we don't know how to analyze them to get that.
It's still possible that they do.
Yeah, so what we know is that if the evaluation points were chosen randomly from a large field, then we get such properties. But for a general case, we don't. And we don't know any explicit evaluation set with such a property.
I thought there are some bad ones too, right? Or is that like?
There are bad ones, but they don't correspond to the list decoding example. They correspond typically to the list recovery example, which is a generalization that we won't get into.
So for all you know, for any set of evaluation points, this holds.
Yes, yes. For all we know, that could be true.
So sorry, we're saying this is like list decoding because like if you look at this as an average, then there's one.
Right. So yeah, I'm going to comment on that. Yeah. So first of all, for S equals 1, this just means distance because it's delta G H1 plus delta G H2. Sorry, H0 plus H1 is at least 1 minus R. That's just triangle inequality once you have distance. So it goes both ways. These two statements are completely equivalent. The first is our usual definition of distance. The second is this ball version. This implies this by triangle inequality. From here to here, you just take G equals H0. Okay. So why are we interested in this? Because what I can think of this as is the sum version has an expectation version. And if the expectation of such distances is more than S over S plus 1, then it means that the maximum out of these would be definitely more than S over S plus 1. So if we take any S code words like this, they can't all be in the ball of radius S over S plus 1, 1 minus R. So what this will allow me to conclude in line with that is So no Hamming ball of radius. My radius has increased now, which is what I wanted to do. But in the process, I have to pay this cost of S over S plus 1. And in some sense, we need this because you can always generalize this example. We had two things here. You can take 3, 4, and so on. S plus 1 such things. And again, build this G with a common part here and 1 over S plus 1 fraction from each.
Sorry to be annoying.
Yeah.
Is it supposed to be a sharp inequality?
Uh,
S plus 2 or more?
I actually will do something even worse. We'll just add we'll not be able to achieve this exactly. We'll add a slack term. So what we will do is this is what we will eventually actually achieve for any epsilon greater than 0. Okay, but this is all setting out the goal. This is the kind of property we want from a code. I've not told you anything about what that code would look like. The hope is that because Reed-Solomon worked for S equals 1, maybe some variant of that will work. And we'll work towards that. Okay, now that I've set out the goal for Act 2, in Act 1, we'll consider the special case where you can always assume H0 is 0 just by shifting all the code words. Right? Every distance is like if you shift each of the entries here by some fixed H0, all the distances don't change. So this is similar to how we prove things for Reed-Solomon, where you assume one of them is 0 and then the other code word is just non-zero. So let's assume H0 is 0. And what would we want in Act 2? That we want H1, H2, Hs to be all distinct, and that should be enough to prove what we want. Here we'll assume something stronger. Explicit. They're clearly non-zero. So we'll get the same conclusion, but we'll have this extra assumption that not only are these H0, H1 up to Hs distinct, they are linearly independent. So of course, this linear independence implies distinctness, but this is a stronger assumption and it will be easier to prove. Okay. Once we prove it with the linear independence case, we'll see how to modify the proof to get the general distinct case.
So you're only talking about finite fields now, not as general sigma. Or
This is just the goal. This is the kind of code we want to construct. I'm happy with any sigma like this. What we'll end up doing is with a finite field alphabet.
yeah, well, does it need to be linear independent, you think?
Okay. Yes, you're right. I'll be dealing with linear codes. Okay. Yeah, I guess this makes more sense once I describe the code. Okay. And the key tool that we are going to use is something called the Wronskian determinant, or a folded version of this. So if I have S polynomials, F1, F2, these are all univariate polynomials, then the Wronskian determinant is also a polynomial that is given by Okay. So I take S different polynomials. They need not be different. For any S polynomials, we can define a new polynomial that is just the determinant of this matrix here. The matrix, each entry is a polynomial, a univariate polynomial in X. So the determinant in general will compute to some univariate polynomial also. Okay, so this is called the Wronskian. If you replace this f1 gamma x by derivatives instead, that's the usual Wronskian that's used in differential equations, etc. This is the folded version. And here, it's important that this gamma is primitive. And the key claim that makes this Wronskian useful, so this is our definition.
If you want to add the word determinant,
Yes. Square bracket versus, determinant of that matrix. The key claim why this matrix is interesting is that it captures the linear independence of the polynomials that we are talking about. Okay. So the Wronskian will evaluate to the zero polynomial if and only if the polynomials f1 through fs are linearly independent over the base field fq. Okay. So one direction here is easy to see. If these are linearly dependent over fq, then there is some linear combination. You can use that to get that the determinant should be zero. The other direction is more interesting. Is the statement clear?
Oh,
Before-
do you mean equal or not equal to zero? If only if they're linearly independent.
Yes, I mean not. Yes. Thanks.
The other direction is the same, right? If the columns are linearly dependent, then you can push that to the corners.
Yeah, no, the problem will be that if the columns are linearly dependent, then you get a vector in the kernel, a non-zero vector, but that vector will be composed of polynomials because you are working over polynomials. I want linear independence over fq. Yeah. Okay, but the other side is also not bad. So because now we assume that, let's say, f1 through fq are linearly independent, then you can subtract one from the other so that these fi's all have distinct degrees, distinct leading monomials. Okay. I can change all these polynomials into fi being some non-zero ai with x to the di and then remaining terms. And the di's are distinct. Right? Once we have that form, just look at the leading monomial of this term, of this determinant. The leading monomial would look like 1 gamma to the d1, gamma to the d1 square, and so on. Second column will look like 1 gamma to the d2, gamma to the d2 square, and so on. So let me write that down. once we assume that these are distinct degrees, which you can always do, let's look at the leading monomial. Its coefficient will look like this determinant here. And this is a Vandermonde determinant. It's non-zero if these entries are all distinct. Because we chose gamma to be a primitive element and D1 through DS are distinct, we get that these points are also distinct.
How did we get to this determinant?
So let's just keep track of what the highest degree term is.
Meaning we changed the FIs to be just monomials.
Not just monomials, just different leading terms.
No, but we might as well think of them as monomials if you are looking at it.
Sure, yeah, I think you're right. Yeah. So let's just think of them as monomials. In that case, the term here will look like gamma to the D1 with x to the D1.
Right.
And then the next term would be gamma to the 2D2, x to the 2D2.
Right.
If you collect all the x's separately, the constant next to x term will just be this.
Next to x to the power 1.
Next to, no, all the x's that we get.
The first column is responsible for x to the D1. The second for x to the D. Right. You are looking at the highest degree term of the determinant. Its degree is D plus 1 plus D2 plus.
Like the point is that the highest degree of the determinant is like the product of the highest degree monomials in all the.
Yeah.
And therefore, you want to prove that it's not zero. It's sufficient to show that this term is not zero.
Yeah.
Right? Am I following?
Yeah, that's good.
Okay.
So do you get some sort of constraint like regarding the characteristic of Q for this to work or something?
No, so primitiveness is sufficient. If you are working with the derivative version, then you need that characteristic condition.
And you don't need S less than or equal to Q or anything like that?
Yeah, S is much
Even
smaller.
our linearly independent implies that, right?
Yes, yes. In fact, I'm thinking of S as much smaller. I'm thinking of S as something like 5 or 10. Okay, regardless, all we need is this claim. So that motivates why we can do Act 1 separately, because Wronskian is well suited to deal with the linear independent polynomials directly.
Sorry, so then this claim is true just for functions, any functions over the field, like as in, I mean, just by interpolation?
I think so.
Okay.
Yeah. Okay. Right. So I want to use this Wronskian, and I have linearly independent polynomials coming from my assumption. The problem is that in each column, I have these S values. Now, assume that, let's say we are dealing with G, H0, H1, H2, and so on. If there were two columns here that both agreed with the same G, all of the values here, then I would be able to get a root for the Wronskian. So I'm just trying to do some wishful thinking here, that if there were two columns, say F1 and F2, both agreed with G, add x equals 1, add x equals gamma, like add F1 of gamma, add F1 of gamma square, and then same with F2, F2 of 1, F2 of gamma, F2 of gamma square. If the entire columns were equal, then I would be able to say that there is a root of the Wronskian at x equals 1. right? It is non-zero because I've assumed these to be linearly independent. There is a root, and then I can try to use that to bound, because it's going to be, again, a bounded degree polynomial. So how many roots can it have? It can have s times the degree of f. So that's the plan. But to enact that, I need to guarantee that all of these values will be equal, and all of the second column's values will be equal. And this motivates our definition of folded Reed-Solomon codes. So in the folded code,
First, it was powered body or
Right, okay.
Right.
right. So the folded code itself appeared in who used this to get they were able to deal with Hamming balls of radius as close to 1 minus r as you want. There was a precursor to this, which was Parvaresh-Vardi, which did not have this folded Reed-Solomon structure, but it was closely related based on taking powers of polynomials with some modulo irreducible. And I think this may have appeared even before for some random channels. Okay. The code modification is simple, that previously we were saying each polynomial, let's say the polynomial again would be, we were encoding it as now we are going to change the encoding to, this was the Reed-Solomon encoding. So we take all the n evaluations, but bundle them differently. So the first S evaluations here, F1 through F gamma to the S minus 1, I call them a single new symbol. And that is going to be an element of FQ to the S. Likewise, the second symbol will be the next S symbols and so on. So this decreases the block length by a factor of S, but increases the alphabet size by a factor of S also, powers up the alphabet size. It's not too difficult to check that the distance does not change, the rate does not change, everything is same, but we'll get a boost in terms of this list decodability properties. So this feels a bit like cheating, but remember, eventually our goal was that we just wanted to construct a set over sigma to the n. So the sigma has changed now. Ideally, I need to define what linear, etc. means over this FQ to the S, but it just means that you unfold and then do linearity. Okay. So when I say linear independent, I'll still be thinking of these as FQX degree less than K polynomials.
Another way to say this is that you're allowing only a more restricted error pattern.
Yes, exactly. Yes. Yeah, so this just changes the Hamming metric that I'm using. Previously, I was saying that each coordinate where things change, I'll count that as one error. Now, no matter how many differences there are in a block, it just gets counted as one. So if you prefer to think of it like that, we are just changing the metric on the same set.
You said I should think of it as like 10 or something like that?
Yeah. But this change allows me to use the Wronskians more efficiently. Right? Because now what I can say is, if G agrees with a code word in coordinate number 1, it means that G agrees with all of these positions. And if it also agrees with F2, that means all of these positions are common between F1 and F2. And that I can try to use with the Wronskian. So the Wronskian directly motivates this folding operation. Okay. Suppose these are my S polynomials. Now they're folded. There are S symbols in each place here. There are capital N such coordinates, which is N over S. Okay. By the way, I should mention that when I do this, the rate is still K over little n. That does not change at all. I'm just changing the metric, etc. Okay. So if I write down all the S code words like this, let me mark out where it agrees with G. Maybe in the first coordinate, H0 agrees, H1 agrees, and the rest of them don't. In the second coordinate, maybe HS agrees. And in this one, maybe only H0 agrees, and so on. Right? So there are S code words. There is some G. This is adversarial. It could be anything. What can we get out of the Wronskian for this condition? Okay. So let me just define. These are very natural definitions. AI subset of N. Improv. AI is just where I'm marking these agreements. All the locations of the circles, A0, A1, up to AS. Right? Sorry, I meant capital N here. Right? Because I'm thinking of only the folded symbols now. And BJ is the same set, but looked at row-wise. Okay. So, um, Okay, these definitions might be more confusing than what I'm trying to say. I write down all the S code words and mark out where H0 agrees with G. And I just circle those coordinates. Even if one disagrees, I'll not be circling it. If there is a circle, it means that all of the S symbols here agree with G. Same with H1 up to HS. Then there are two ways of looking at these circles. I can look at them column-wise or row-wise. Column-wise, I get S plus 1 many sets. Those are called AIs. Row-wise, I get BJs. There are capital N such sets.
So BJ just tells me which agrees with G on the jth column.
Yes, exactly. Exactly. Okay. The claim is that if Bj is some little l, then I get L minus 1 many roots for the Wronskian. Okay. In fact, I'll tell you exactly what the point of what root that is. So if Bj is L is going to range between what? 0 and S plus 1. Because this is a subset of 0, 1 through S. It's going to range between 0 through S plus 1. Well, I guess let's ignore Bj being 0. But if it is 1 or more, then I get L minus 1 roots here.
So, stupid question. The Wronskian is with respect to whom? Like who are the polynomials we put in the Wronskian?
It's going to be H1 through HS.
Okay.
And because I am only working under the assumption that those are linearly independent, we know that the Wronskian is a non-zero polynomial.
Sure. Oh, okay. Sorry.
Right? So that's all I'm using.
I cannot read what it says over there. So if Bj equals L, then what?
Then there is a root with multiplicity L minus 1. There is a root of the Wronskian. There is a root of the Wronskian with multiplicity L minus 1 at comma to the Sj, if I'm not wrong. So why is this? Let's justify this quickly. Let me focus on a fixed J, any column, any row. If I have L distinct circles here, suppose H0 was not in these circles, then maybe let me write it separately. Then the Wronskian of these S linearly independent polynomials evaluated at x equals 1 is simply this. I just remove the x's from each of the entries. Okay. Now, if there are L circles here, not including 0, then that means that there are L columns that are all looking the same, exact same. As soon as I have two columns that look the same, I have a root for the Wronskian. Right? The determinant becomes 0. In fact, if I have 3 columns that look the same, then I have a root with multiplicity 2. Because even if I take a derivative, in each of the terms in the derivatives, you'll get 2 columns that are equal. So if there are 5 columns that look the same, I have a root with multiplicity 4. Okay. There's this annoying case that H0 might also be it. In that case, even if I have Bj, the size is L, so there are L minus 1 things here, they all look 0. So again, I get L minus 1 roots because L minus 1 columns become 0, not equal. So in either case, I get L minus 1 multiplicity for the value. Here it is x equals 1. In general, if you're working with Bj, it will be gamma to the Sj. Okay. Maybe Sj minus. I'm indexing from 1 through n.
Why is the root in this point?
The root is in this point because so if I'm dealing with, let's say, the second row, then I'll have to look at indices from gamma to the S to. Yeah. And these are distinct points. So of course I can add all of these roots up. And together the root should not exceed the degree of the polynomial that we have constructed.
The roots counted with multiplicity.
Roots counted with multiplicity. Yeah, so the multiplicity here is very important. By the way, there is the case where L is just 0, but that actually should not happen because Bj being 0 is G does not agree with anything here. Why should I even consider such a G coordinate? I should make it agree with one of them. Otherwise, there's no point. Okay. All of that was to say that if I sum up Bj minus 1, what is the degree of the Wronskian that I have? It would be S times the degree of each polynomial. Right? Because each polynomial has degree less than k. And when I take the determinant, that blows up the degree by a factor of S. The degree of each polynomial was Rn to begin with, and that remains the same. And this here is equal to summation AI. Because AIs were just the column sets that I defined. That's just double counting. And now if you notice.
So distance is 1 minus 3.
Exactly, yeah. Okay. I define AIs to be the agreement set, so of course the distance is 1 minus of that. AI.
And L minus 1. So 1 minus AI.
Yes, it should not be 1 because AI does not make sense. Yes. Um, Okay, I get this. And now if I just do the averaging part, okay, so at this point, it's just some computation. It's not important. The point is that if you look at this expected value, which we wanted to be S over S plus 1 minus R, we almost got that, except for this little s factor that comes from this normalization between capital N and little n. Because the block length changed, it's off by a factor of little s. So up to this little s, we got pretty much what we wanted.
So it works only for low rates.
Sorry?
It works only for low rates. You cannot do this trick if the rate was half.
Okay, yeah, so right now it seems like that is true, but there is a trick to get past this. But before that, is this clear to everyone? Like once we bounded summation bj, everything else was just usual computation. So the key point was that we were able to leverage the Wronskian to get a bound on the summation bj and consequently summation ai.
So in some sense, this is the generalization of the proof for distance for it. So
Yeah. Okay. I'm quite slow, so let me pick up the pace. This right now it seems like, as Avi pointed, that you can only do this for small rate, but actually there is a way to get past this, which is right now I was folding only S things. Let me fold even more. I'm not losing anything by doing that. So let's increase this folding to some M, which is much, much greater than S. But the Wronskian, etc., I'll still analyze using S. So there is this decoupling that I do, where I fold much more, and then I take a sliding window of size S and do the Wronskian argument. If you do that, this S here can be replaced by so previously M was just S, that was giving us S, but in general it can be replaced by M over M minus 1, S plus 1 factor. So if you choose M to be much bigger, then this is lossless. You lose some epsilon, but nothing else.
I'm sorry to slow you down, but can you explain this a bit more? So
Sure.
I'm thinking of S is fixed, even 3 or something
Yes.
like that.
So
M is large. How does this help?
right. So now we'll again draw the same diagram. M will be large, but I'll still maintain Wronskians of sizes. So Wronskian is still probably 3. I can take a bunch of sliding windows here. they will all look like 1 gamma gamma square. The next sliding window will be gamma gamma square gamma cube. Next one gamma square gamma cube gamma to the 4 and so on. So for each such window, you can do all of this argument. So the multiplicity here will grow from just L minus 1 to L minus 1 times M minus S plus 1.
So it's not the multiplicity, you just get more roots. So this
But they're
yeah, sorry, yeah, yeah.
overcounted. But you're overcounting.
No.
Average.
I'll get multiplicity L minus 1 roots, add gamma to the S times J minus 1, and also the next point to this. So gamma to the S J minus 1 plus 1,
Oh, I see.
and so on. So I get a factor of M minus S plus 1 extra here. And that will get then balanced by M. It's slightly magical, but it works out. The trick is just the sliding window.
So you lose in the alphabet size.
You lose in the alphabet size, yes. So all that cost is passed on to the alphabet size. But if you only care about rate, distance, etc., that doesn't matter. Even the alphabet size is not too bad. You typically choose S to be 1 over epsilon. M can be chosen to be 1 over epsilon square. Right? So, yeah, maybe this is worth mentioning. You end up choosing S to be 1 over epsilon and M to be S over epsilon. So that everything gets down to a 1 minus epsilon factor. And this sliding window thing we'll see again. I'll not go into the general M thing because that's just another parameter to keep track of. I'll work with the S folding only. Okay.
Want to take a break?
Yeah, should we take a break? Maybe, yeah. Okay, so now we'll go to this Act 2 where the linear independence is taken away from us and we still want to prove the same thing. So even if you got lost in the first part, this is the time to come back. And it's not clear what to do at all, right? Because the Wronskian is what we were using.
Can you modify the polynomial to increase the block length a little bit to make distinct into linearly independent?
No, the polynomials, linear independence, etc., is just coming from the polynomial structure as
It's coming.
degree k.
Yeah. Okay, good.
So again, I'll assume that H0 is 0. And this rank of these polynomials is P less than S. Okay, so here's the idea that partition to okay, so the rank is small. It's P less than S. If it was equal to S, we just dealt with things. If it is small, let me try to work with what I have. I'll partition this set of S things into P parts such that if I take any part from first H1, any polynomial from H2, any polynomial from HP, I'll get P different polynomials. These should be linearly independent. This you can always do greedily. Like find there should be a basis of p things, right? Let me find one polynomial, and then if the next one is in the span, I'll keep putting it into H1. And if I find a linearly independent one, I'll start a new H2. Okay. We can do this a little more explicitly also. So let's say, without loss of generality, let's say H1 through HP was a basis. Then any F in this set, H1 through HS, can be written as summation alpha j HA. And we partition based on
Non-zero.
we just look at the last non-zero coefficient and partition based on that. Such a thing will always have the property that no matter which code word I select from HI, the collection will always be linearly independent. Okay. So this is just elementary linear algebra. You can do this greedily. Now, for each such collection, F1 through FP, I can do the same argument as before. What will I get? There will always be this annoying H0, but after that, it will look like so P plays the role of S before. These are linearly independent. So this is all okay. It's just black box appeal to what we did before. Okay. But I'm going to prove something stronger. Okay, so first this notation, delta G capital HI is the set of coordinates where G just does not disagree with one H code word, but all of the code words that we see in this set HI.
Say it again.
So HI is a set of code words. Each code word will give me a set of coordinates where G and that code word differ. I will take the intersection of all these coordinate sets. So I'm looking for the set of coordinates where G differs from all of them. Okay. Slightly weird definition. So I will strengthen from this statement, which was easy to show, to this. Clearly, this is a strengthening because this delta GHI is always dominated by delta GFI. It's just the intersections. So I'm showing a smaller quantity is also large. Okay. Is the goal clear? And won't go into all the formal details, but the idea is quite simple. You start by noticing that the Wronskian, even though it's written for polynomials, it's really not a property of polynomials. It's a property of their span. Because I can always add or multiply by scalars and add two polynomials together, etc. So the Wronskian only depends on the up to constants. It only depends on the span of the polynomials that I was dealing with.
Can you say a more explicit statement? The Wronskian is itself a polynomial. So what do you mean by it depends?
Just replacing F1 by F1 plus F2 plus F7 doesn't change.
Yeah.
I mean, you can add it, right? I mean, the determinant doesn't change by if you add columns to other columns.
Okay.
So you can replace this set F1 to Fs by any other S linearly independent polynomial in their span.
Yeah. Okay.
Right.
Like it's important that the span is over Q. Like if you do it,
Yes.
Yeah.
Yes.
Yeah.
Yes.
polynomial.
Yes. So the span, etc., is all over FQ. But yeah, so you take any subspace, it doesn't matter which basis I take, I'll get the same polynomial as the Wronskian, up to constants, like up to scalars. So what that means is that all of these F1 through FP that I construct from the Cartesian product, H1 cross H2 cross up to HP, all of them share a Wronskian, right? They don't have different Wronskians. So previously I was proving this for different F1 through FPs, but they are actually sharing the same Wronskian.
Wait, I'm not sure I understand. You're taking the Wronskian of S things or of P things?
I can only take off P things because S is linearly dependent, so I'll start getting 0.
So you're taking of P things, and you're saying in capital H1, you can take F1 or you can take F1 prime.
Yes.
It's going to be the same?
It's going to be the same because the span of all of these is same. The span of all of these is just the span of the basis that spans them.
Oh, okay.
Okay. So all of these Wronskians will be the Wronskian of the canonical first P things.
So this is saying once you agree with something in that span,
Uh-huh.
that should be counted as a root of this shared.
Exactly. So I should do a joint argument with all of these F1 through FPs because the polynomial is shared. And what that corresponds to is, recall that here we had AI as the agreement between G and HI. I can take union of agreements because no matter which HI agrees, so I will define AI the union of agreement sets for all the code words in this capital HI set. It doesn't matter which, so when I was drawing these circles, it doesn't matter whether F1 gave me this or F1 prime gave me this. Because the Wronskian is shared, I can still get a root, which is all I cared about.
But it's not, I mean, the picture is not this picture anymore.
The picture, yeah, so the picture will now have capital H1, capital HP.
Yeah.
But I can still draw circles based on the union, like whether even one agrees or not. And the key observation is just this, that the Wronskian is shared. Okay, if I take union here, that means that I get intersection of the distances on the other side. Like the complement of this will be the intersection of distances, which motivates this definition. So I do the same argument as before, and I will end up at this. Right? So this was a strengthening, but it was hiding in plain sight. All we had to do was observe that the Wronskian is shared, and you take the union of agreements instead of intersection. And this, I claim, is strong enough to deal with the goal 2 directly. So let me show you why. So let's recall the distance case that we had, very basic triangle inequality. For Reed-Solomon codes, we said this, right? Delta GH1 plus delta GH2 was more than 1 minus R. How do we prove this? You have H1, H2, maybe they agree in some R fraction, not more than that. So wherever they disagree should in total cover, in union cover 1 minus R. So like G might, let's say, so if I have shaded the disagreement area, then the union of these should cover 1 minus R. Because in this set, I can't be agreeing with G on both sides. Because H1, H2 are different here. So at most one of them can agree with G at a time. So it's the union, but I could have subtracted an intersection also. If there is a coordinate where G differs from both H1, H2, I should subtract that. Because I have essentially double counted it. Where I'm using the notation that I defined there. I look at the common intersection, and I could have always removed this. This is for free. Or if I just rewrite this, there's always this extra term that I get. And I can use this as my inductive hypothesis now. That not only will I get the S term inequality, I'll have this extra term dangling here. So I'm going to use induction on S. And the statement is going to be this is what we had before, and I've strengthened this a bit. Okay, so strengthening of the induction. Clearly it holds for S equals 2. So S equals 1. Fortunately, I'm indexing from 0 to S. Okay, so my base case is clear. I need to prove the inductive case. In general, I will start with a set like that, H0 being 0 and then H1 through Hs. The rank will be P. I partitioned them into H1 through HP. And now I use inductive hypothesis on each partition separately. Actually, we are about to prove this. Maybe I'll use this.
It seems to resemble that the
Yes.
expander.
Yes.
Is.
So the proofs are very similar. And I don't know why.
Don't know why.
Yeah, like the codes look very different.
Something about the logic of distances, agreements.
Yeah. Okay, yeah, I'll also mention something once we finish this.
So I mean, I remember already being confused when you showed the expander proof, and it's heading that way.
Right.
So, is it useful to think of like just one step above the distance case, like S equals 2?
Actually, it's, I think, better to see the general case, and then we'll point out the 3 case.
An explanation to this discussed later on in the class. For those who don't remember the expander-based proof.
I'll just go to the video on
You're giving me homework. No, I'm kidding, but like it sounds interesting. So maybe, but maybe later.
I mean, yeah. Okay, let me just finish this proof and then I'll get to that. So, I've just partitioned the sum according to these HIs. And then on each HI, I use inductive hypothesis. HI will be smaller than.
HI, and each capital HI,
Yes.
you use the inductive hypothesis,
Yes.
which means
The inductive hypothesis will allow me to say that it's at least S times 1 minus R, like the number of code words minus 1 times 1 minus R plus this common term.
is there an interpretation we can have in mind for what this means?
I mean, if you ignore.
There's some savings, you get this extra term that.
Yeah, so if you remove the extra term, then that was just what we started with, the average radiusless decodability. And this extra term, like in the triangle inequality case, it was just out there and we were ignoring it. We are saying there's always this extra term that you can add. It's saying that if G was differing from everything, there's no point really looking at those coordinates.
Right.
I don't know if that is
You want to get back those coordinates.
Yeah, so if you think in terms of folder read Solomon, etc., let's say there is some G, some coordinate where G does not agree from anyone, then I should think of them as erasures. It's as if those points never existed. Okay, so then you'll subtract that term from here, but there will be some offset, and that offset ends up there. So you should think of them as erasures, or the points almost never existed, kind of. So this would be by inductive hypothesis. Okay, so once you partition the sum into these partitions H1 through HP and use the inductive hypothesis, we'll get these dangling terms from each of the inductive terms that we used. The remaining terms will nicely sum up to S minus P because this is a partition. There are P parts. So that term sums up to S minus P. And the dangling terms, we can combine them together and use the Wronskian argument that we just talked about to get a P minus a P times 1 minus R there.
A good special case to consider is when each HI is the same code word repeated many times. Then, then it's clear you have these properties here and the intersection is full. So it just.
No, so you do want the code words to be distinct. Otherwise, this is hopeless.
Yeah, no, I meant multiples of each other.
Okay, yeah, yes, it's a one-dimensional space.
One-dimensional space. Yeah,
yes. Yes. So there it becomes much easier to prove, but
it's a much easier thing, but maybe it gives the intuition of what happens. Or not.
Wait, I'm confused. Shouldn't we have proven a stronger statement? Like S?
Yeah. So to make the induction work, you need to prove the dangling term appear here also. Is that what you mean?
Yes.
But you can believe that works. Believe me that works. Like,
but you are cheating. So.
Yes. So ideally, yes, there should be a delta G of two H's here.
This like appears from like all these dangling terms have like this. They're like double.
Yeah,
some
exactly. Like if some coordinates are not appearing in any one, then I might as well delete them to begin with. So the real dangling terms here should be the ones that are not appearing here. Okay, maybe this is a good time to do some of the history because this is not my proof. So for read-solving codes, the first decoder was given by Welch. This was in the 70s. Then Sudan and Guruswami in late 90s gave list decoders for read-Solomon code that work up to so-called Johnson bound. So that means that for read R code, they work up to 1 minus square root R. And this is still the best known for arbitrary read-Solomon code. We don't even know if the list is bounded beyond this radius. This is less than 1 minus R. Then people wanted to get to 1 minus R because that's the best we can do. Parvareshwardi gave a code that looked like this. Basically, it worked for small rates, but not very well for general R. For small rates, it did pretty well. It would approach a 1 minus R. And then Guruswami and Rudra in 2006 gave the folded read-Solomon where you can get arbitrarily close to 1 minus R. The next thing we'll see is an algorithm, and
they also had to handle the non-linearly independent case. What did they do?
No, they did not. So, okay, I should probably mention that. So, when we only had the H0 to HS being linearly independent, that already implied something very nice, that the list should be an affine space of dimension S minus 1. Because if it was not, if it was larger, then I'll find S linearly independent guys after removing H0. And that is where, for example, Guruswami Wang stopped.
So, subspace evasive sets in where introduce that.
Yes. So Guruswami Wang, they were able to prove this 1 over epsilon dimensional affine subspace result that I mentioned. And then the natural thing is that you can try to use subspace evasive sets to reduce the list size, etc.
Wait, what does the statement say? 1 over epsilon dimension.
Right. So actually, let me be a bit more explicit. For S over S plus 1, 1 minus with everything, with this radius, the list is contained in an affine space of dimension S minus 1. The act 1 that we saw essentially proves this. Okay. And this proof where we can deal with just arbitrary distinct guys actually gives a, so this gives a list size of, yes, q to the 1 over epsilon, q to the s. With the distinct proof, you can get a list size that is optimal. So that's a big jump. And this second act that we saw is due to Chen and Zhang. Their proof was written differently. This is like probably more in spirit of the expander-based codes that we saw before. And
wasn't there something like in between that it made some argument of like with subsampling or like a
yeah. So we are going to talk, yes. So this is only in terms of combinatorial results. This result was algorithmic. It will give you a basis for an affine subspace. There was the Koparty, Ronzevi, Saraf, and Wooters result that said that one, you can reduce the list size from q to the 1 over epsilon to 1 over epsilon to the 1 over
But
epsilon.
the subspace designs of Western,
They also
was earlier than this.
Yes, that's right. But this was more interestingly an algorithmic technique that not only is the list size better, because maybe in the subspace evasive sets also they could do algorithms. But they gave a way to prune this subspace better than. So we now know that the list size is 1 over epsilon. You're given this 1 over epsilon dimensional subspace. How do we go search over that space? And the KRSW result was a way of doing that. I mentioned this because this is going to motivate what we discuss next, where we are trying to find a subspace and find these list code words efficiently. It's not very comprehensive.
Wait, you can't find the subspace itself just with algebra, or
You can. So that's going to be our act 3.
oh, okay.
But with the channel and flag, we don't really need.
The Chen and Zhang result is not algorithmic. Because this distinctness argument, etc., it's not clear how to algorithmize that. In fact, from what I've described to you, it's not clear how to do algorithms at all. The original algorithms were based on bivariate factorization, etc. But in 2011, Guruswami and Wang, they found nicer algorithms that just do simple linear algebra. And the idea is simple. Think of a polynomial that looks like this. multivariate polynomial where the y's are linear. The total degree of y variables is linear, is 1. So we are trying to get algorithms for folded Reed-Solomon code, for which we already saw. So this is sort of an algorithmization of the first part where we had the linear independence condition. Okay. So we imagine such a polynomial and we ask it to satisfy a bunch of conditions. The conditions just look like, we look at the ith folded symbol. The ith folded symbol was indexed from s times I minus 1 up to s times I minus 1 plus s minus 1. You feed all of this s size symbol into these y variables. Okay. We had s folded code words, so we had s symbols to go with. If this was correct, then this would actually look like some polynomial evaluations. But we are not given such a polynomial. We are given this g, and we are expected to output the bunch of code words that are close. Okay.
You want to say that this number of conditions allow to find
Yes.
the non-zero Q
Yes.
with some degree.
Yes, exactly. So an obvious choice for such a Q is always all zero, but you make the number of variables high enough so that there's a non-zero solution. Any H? So the second step is to argue that any H close to G will satisfy this as a polynomial equation. So G is supposed to be a proxy for H, right? If G and H are close. We are saying for the coordinates where G did agree with H, there the equation would have looked like interpolating for H itself. But there were some errors. You can still end up arguing that even if we started from an erroneous interpolation condition, we get something that is true for all true code words.
Like 0 on too many points or?
Yeah, essentially. And then the third part would be say that there can't be too many H's like that. So this proof will exactly be similar to what we saw before. But algorithmically, there are just two linear systems to be solved. The first one is a linear system where you find the A0x, A1x up to ASX. The second linear system is going to be, you think of the variables as H0, the coefficients of H polynomial. And because this is all linear, you'll get a linear constraint. If you write down this polynomial equation, you'll get a system of equations involving the variables H0 through Hk. through hk minus 1.
So there is no factorization.
There is no factorization. It's just two linear systems. First to find these A0 through AS, second to find this H. In fact, all of this can be done in quadratic time. And now I think near linear time.
Step 2 uses some resolution or 3, I mean. Yeah.
Step 3 will just use the Wronskian.
So step 2.
Step 2 will just use degree, bounded degree, and the number of roots being nice. Yes. Yeah. So Bezu, I guess, will not show up. We do start from this multivariate thing, but here at this point, it's all univariate.
So it's a linear system, so it will have a subspace as a space of solution, right?
Yes.
The subspace of H.
Yes.
You want to say there are much fewer than satisfied.
Yeah, but for now, we are not worrying about that. That is still Act 3
This is still Q to the 1.
Yes. So I'm okay with finding a subspace at least because until now, even that is not clear.
Wait, what are you saying? We get a subspace of Q's or H's?
For H's. You actually also get a subspace for these A0 solutions, but you take any non-zero one.
Okay.
Don't use that. So the first one is simply, I need to specify what the degree is. Let's say the degree for this is T. And I hope to eventually substitute a degree K minus 1 polynomial here. So I'll choose this to be degree Rn so that when I substitute, everything becomes T plus Rn. So the number of variables becomes T plus Rn. And again, I'm being a bit sloppy with plus 1 minus 1. S times T. I want this to be more than capital N, which is the, think of this capital N as capital N over S. If the number of variables exceeds the number of constraints, then we are good to go. We'll find some non-zero solution. The second one will say how many. So we look at this Q, X, HX, H gamma X. As Avi said, this is a univariate polynomial. What is its degree? Its degree is going to be T plus Rn. So degree of Q after I substitute. If I get more zeros than the degree, I know that this has to be 0. How many zeros do I get? Well, it depends on the agreement between G and H. So we had this. This was the lossy version when we did not substitute M over F minus S plus 1. The corresponding agreement is going to be 1 over S plus 1 plus S square R over S plus 1. I guess we don't even need that. We should just get it out of here. Yeah, we'll see that same term come out here. So what is T? Right, so from here, it's plus 1. Which is same as the radius there. So my point is that the radius that we saw before, if you do this interpolation, you'll get the exact same thing. And again, you can do the sliding window argument that we saw before and get close to capacity.
So is this a different proof, or are we still having to think about the Wronskian?
There is one part that is left, which is how many H's can you have? Because right now there's no bound on that. It's a multivariate polynomial, so it can have a lot of zeros. Actually, it turns out it can't, and at that point you should be using folded Wronskians, right? Because until now we have not used that. We needed Wronskians to prove the affine subspace result. So in the third part, we use that. And all you say is, so I'm looking for H's that satisfy this condition, right? Suppose these H's are again, I need to deal with the affine thing, so I'll just assume the second one to be H0 plus H1. I just subtract H0 from each one. Then you take any two solutions. Let's say there were S such solutions. You take any two solutions, let's say H0 and H0 plus H1. You'll get a new constraint that looks like and I claim that this already implies that H1 through HS are linearly dependent.
I don't follow what is this constraint, A1, H1.
Yeah, so I'm just thinking of multiple solutions to this system and subtracting one from the other. So this A0x goes away. And I'm left with A1x times subtraction of two solutions. So to make it easy, I've just assumed the solutions themselves to be H0, H0 plus H1, H0 plus H2, and so on. So that the difference looks like H1x.
It should be H1 in all of them, right? Not H2.
Yeah, it is H1. Yeah.
Right.
And I claim that this already implies that, so this is true for H1, H2 up to HS. This already implies that H1 through HS are linearly dependent. And why is that? Because I have found this linear combination in the polynomial ring. So the Wronskian must have determinant 0. Right? So if we have the Wronskian. Yeah. We are combining all the H1 gamma x up to H1 gamma to the S minus 1. So the A0 through AS vector will look like a row vector that is we are multiplying from the left, and it is non-zero. So what that means is that this Wronskian will vanish, and so they must be linearly dependent even over the finite field FQ. If these were scalars, then we would directly be done. Sorry, I take it back. If A1x, A2x, etc., they are polynomials, but the Wronskian allows us to transform polynomials to just scalars. When this was discovered, there was a more direct proof for this, where you can think of Hx, and this is again a linear system. You think of the variables of the monomials of H. H is composed of monomials, right? H0 plus H1 up to Hk minus 1. So each monomial here in the system will give you a new constraint on the same system. And it will be a diagonal matrix. You just look at the diagonal of that constraint system. And you can argue that it can be 0 only some S minus 1 times. But with the Wronskian, it's even simpler. So what all of this does is that it starts from G, it gives an affine subspace, maybe it gives a description of a basis that contains every such possible solution in G. Okay, and finally in part 4, we want to talk about, is this really the best we can do algorithmically? So the problem here is that because we are solving only linear systems, you can't get rid of two code words and their linear combinations from their appearing. Like the algorithm can't distinguish between two genuine code word solutions and their linear combinations. So we have to deal with subspaces. But turns out that we can do things algorithmically that are much faster. It started with this KRSW work. So now we are given some affine subspace of dimension s minus 1. There's a clear algorithm. Enumerate over all of the combinations, and you'll find your list. That will take q to the s minus 1 time. Almost n to the 1 over epsilon. Can we do better? Because the list is only of size 1 over epsilon. We saw that before. So what KRSW did was, they look at this affine subspace, and G is still in my hand. In fact, their argument works for an arbitrary linear code. Just pick a random coordinate I and hope that this is correct. With decent probability, it will be correct because, okay, so there is some H I have in mind. I is correct for that H. So I hope that Gi equals Hi. I don't know what Hi is right now. And because this is an affine space of code words only, there will be a lot of positions where some basis vector is non-zero. Whenever a basis vector is non-zero, I can reduce the search space dimension by 1. So what does this look like? It looks like and I'm supposed to figure out the values of alpha 1 through alpha s minus 1. Let me randomly sample a coordinate I, and I hope that this entire system, f0 plus alpha 1, alpha s minus 1, this at position I is equal to Gi. This gives a new affine constraint on these alpha variables. If the constraint is non-trivial, then I can reduce the dimension by 1. So you show that with some probability, this is so if you're decoding at 1 minus r minus epsilon, what they show that with probability at least epsilon, both things happen. Gi is equal to Hi and dimension reduces. So when I did this conditioning, H survived, H did not get kicked out, but somebody else got kicked out. So the dimension did reduce by 1. And if you keep getting lucky every time, then with probability epsilon to the s minus 1, you end up with the correct code word because you'll be at 0. And that directly gives this 1 over epsilon to the 1 over epsilon. And then the final thing is that this works for a general linear code. We don't even need folded Wronskian, etc. Like once you have the subspace, this works. In fact, it doesn't even need constant dimension. You can make this work with dimension n and effectively reduce list size from q to the n to 1 over epsilon to the n always. But for folded Wronskian, there's better things. We know that we should be expecting 1 over epsilon kind of list size. And the idea there is that each coordinate does not just give me one constraint. It's a folded symbol. So it actually gives me multiple constraints. So this would look like gamma to the s times I minus 1. And then and so on. So I'll get s different constraint from each coordinate. In terms of getting lucky with gi equals hi, that probability will remain same, but the dimension might reduce from d to much smaller than d. In fact, it can get to 0 in one go. And then again, the Wronskians come into picture. You say that, okay, maybe 0 is too hopeful, but what you can show is that d on average in expectation always goes to from d to r times d, where r is the rate. So it's a much better drop than d to d minus 1. And then you do some induction on top of this.
This is your work.
This is my work. You do some induction on top of this, and you end up with a list with probability at least 1 over sp plus 1. I will output any h that I decided on. And d itself was something like s minus 1. So you get with probability 1 over s square, I'll output h, which implicitly also gives a list size bound of s square, because I'm saying this for any possible h. Those should be disjoint events. And this was my work, and then with students from Rutgers, we were able to make all of this algorithmic. So the algorithm runs in poly s time, or poly 1 over epsilon time, and outputs each code word with probability 1 over s square. So you run it in poly s times, or poly 1 over epsilon times, and you'll end up with the entire list. One final comment.
Tell us something about the algorithm.
I mean, I can, I just don't want to go over time.
Oh, that's okay.
Okay. Actually, once you see this proof d to rd, where does that come from? Like, let's see. So here it is useful to think of the dimension 1 case.
Dimension 1 case.
No, a fine space has dimension 1, let's say. So the real choices I have are alpha 1s. And wherever f1 is non-zero, as I change alpha 1, I'll start seeing different things. So as I vary alpha 1 equals 0, alpha 1 equals 1, and so on, maybe there's some area where f1 is 0 that does not change at all. And then all the other things, everything changes every time. So it's almost like a repetition code. So if I look at where which alpha 1s might appear in the list, the agreement sets here must be disjoint. And this set f1 equals 0 can be at most r.
I mean, this first agreement set is for some age, and
Yes.
the second one is for
Yes,
another
because
one.
these are my candidates, right? Alpha 1s are corresponding to the different candidates. So f1 can be 0 in at most r places because it's also a code word. So remaining 1 minus r is like a repetition code. The first candidate is alpha 1 equals 0. This must be at least epsilon because it will spill over from this r area to r plus epsilon. And the agreement sets will have to be disjoint. So if I have epsilon size disjoint agreement sets, there can be at most 1 over epsilon of them. It becomes more interesting at d equals 2. So there, instead of disjointness, what you get is limited intersection. Because if you condition on one coordinate, I can't say that there can't be any other thing, but the number of things that will intersect here will correspond to dimension equals 1 case. Right. So you get this hypergraph with limited intersections, where the limited intersection come from the inductive hypothesis. And that's the proof. Like if you just keep doing this for larger dimensions while keeping the inductive hypothesis in mind, that will give you a good list size. And
we're looking for an algorithm.
Right. So once you do this, algorithm wise, what we should do is keep track of how much dimension we are reducing. Let me be a bit slow. In the KRSW algorithm, all you do is pick a uniformly random coordinate and condition on that. Now we want to use folded Wronskians. So maybe the natural thing to do is, if there is more rank decrease, I'll choose that. So, because I can compute that, right? That is all something that I can compute. I can go over each coordinate. I can look at the linear system. I can see in this coordinate, d goes from d to 0. In this coordinate, it stays d to d, and so on. But it's counterintuitive. We end up doing the opposite. We say that if the dimension decrease is small, like is d to d minus 1, we increase the weight of those coordinates. Because inductively, the success probability will be smaller there. The problem is if you just increase the weight of cases where decrease is much more, we might miss out on a particular code word that I'm looking for. So there are two things going on. There is some hidden agreement set between G and H. If I pick things uniformly, I am sure I will hit this. If I start messing with the distribution here, I need to make sure I still hit this. If I increase the probability of things, I mean, ideally I want that, right? I'll just always condition on something that takes dimension to 0, and then I'm done in one step. But what is stopping me from missing this set? That coordinate could be a single coordinate sitting here. So I need to balance these two things out. That the distribution should be such that the dimension falls much faster, but somehow the set is not missed.
This is just to find one edge.
Yeah, so I always keep one edge in mind, and my final success probability is just this for any edge. But that is all in the analysis. Yeah, so as I change this distribution, I need to be mindful of those two things. These are slightly, I won't say conflicting goals, but two different goals that I need to balance, where I need to increase the dimension decrease probability, but also make sure that I don't miss out on this. Does this make sense?
Can't you also just find the easiest edge to find and then erase it?
Yeah, but how do you find the first one?
I mean, you seem to suggest that some edges will be easy to find, very fast.
No, it's not
You
clear.
don't know in advance.
That's not clear to me. Like, I
I mean,
think,
if you go always to choose the guy that decreases the rank the most, what will happen?
but it might not correspond to a real, list code word.
Uh-huh. What will it correspond to?
It will be some assignment to alpha 1 through alpha s, but it might not be something that is close to G. Because the space that we are searching over, most of them are far from G.
Right.
We're starting from this n to the 1 over epsilon search space, and we are going down to 1 over epsilon. So most things are bad. We need to get to the right thing. Is this clear that I may want to do this decrease fast, but then I end up in this issue that I may completely miss out on the agreement set. So I want to hold my hands back and not disturb the uniform distribution too much. Because uniform distribution is what allows me to use the size of the agreement set. But you can rebalance it delicately and get the probability to be poly 1 over epsilon.
So for your argument on the left, does that just show that any linear space of some dimension has small intersection with some Hamming wall, like it's completely combinatorial, not about
Yes.
polynomials?
Yes.
Okay.
Yes. Yeah, because if you think of a line, it's really like a repetition code. If you take out the zero part of the basis. So here nothing changes and here everything changes.
I don't think the analogy repetition code is that clear.
No, but the intersection of a line with a hummingbird clearly, yeah, you can bound it, right?
Yeah. Okay, maybe we'll stop here. Yeah, I could have gone into more details here, but I think this might give enough intuition.
Okay, thank you.
One question I have is in the subspace evasive sets,
Right.
which are another way of
Right.
doing that. What you change the code, of course. What is the bound that you get algorithmic results also?
Yeah, you can get this sort of list size bound. You don't get 1 over epsilon.
Okay.
Yeah, so
Subspace evasive set, you make your evaluation points lie on a subspace evasive set.
No. You take a subset of your code. Subspace evasive sets are sets, subspace of there are subsets of the whole universe, which have a few points hitting every subspace.
But how do you encode and decode in this situation?
it comes as a part of the subspace evasive requirement that you
It's
want
not,
to.
you have to.
But it is non-linear, for example.
Yeah, it's on there.
It has to be non-linear.
Yeah, otherwise it just.
Yes.
And who are these? Can you tell me the first names of this Chen and Zhang?
This is Zihan Zhang and Yeyuan Chen.
So what did they do?
They proved the 1 over epsilon tide result that we saw with in Act 2, where we went to distinctness. No, this is the algorithm, I guess.
This is this inclusion, the fine inclusion, exclusion.
Right.
The sizes of the
Right.
one intersection.
Yes, I should say that their proof is phrased differently. This is based on, yes, this is my version of it based on the expander case.
Do you know if their argument can also be phrased as like some purely combinatorial thing, just looking at the intersection size of a subspace and a Hamming wall?
I mean, in some sense, all code list decoding questions are subspace and Hamming wall intersection questions, right? Because
Something, are they strongly using the fact that you're, the specific code, like,
yeah, it's all for folded read
sorry,
summary.
after the information you get, just about, like folded read Solomon code lists being contained in a small affine subspace.
No, from there, it is not sufficient to get optimal list size. From there, you can always get this sort of thing. So KRSW stuff, like you pointed out, is generic. So in general, if you have dimension D and you're decoding at radius delta minus epsilon and dimension is D, then the list size can always be made 1 over epsilon to the D.
I see. So in your argument, you do have to keep talking about polynomials specifically.
Yeah. So I have to keep talking about folded read Solomon. In fact, like this argument that I said, where dimension falls much faster. Like it only makes sense when you have folded read Solomon where there are multiple constraints to work with. In a general linear code, the best you can do is 1 fall in dimension. Folded read Solomon code are very nice in that sense that they allow for more fall in dimension. If the polynomial was everywhere non-zero, then even one conditioning would allow you to fix the coordinate, because you write down a system like this and you invert the entire system, you get all alpha 1 through alpha s minus 1. But that would require this system, this matrix to be invertible. And invertibility of that matrix is directly corresponding to the zeroness of the Wronskian.
Okay, I think I'll take the rest to lunch.